All right, you're back for part two. I mentioned in the last one that I was maybe going to show you a picture of my leg, but I decided I felt weird about that. So if you ever see me in public and I'm wearing shorts, maybe you'll get to see it. But other than that, you're out of luck. Anyways, continuing on, we talked about our main lines for evolution. Let's start moving through these. Our first one is going to be paleontology. So, paleontology is a study of fossils and rocks and stuff like that. Most Actually, no. Geology is a study of rocks. Paleontology is a study of fossils. My bad. We're going to talk about geology in a second. So, paleontology, looking at fossils, we can see modern day traits developing over time in the fossil record. Now, we're going to look at the horse here in a second. But real quick, remember whenever you watched that video about human evolution, one of the things that was mentioned there was that there are large gaps in the fossil record because the creation of fossils is sort of a hit and miss process. Most living things will not ever become fossils. Most things that have ever lived did not become fossils. Only a very small subset of things actually became fossils. So there are some gaps. We don't have necessarily all of the fossils of everything that has ever lived, but we have quite a few, and we have enough to sort of piece together sort of probably what happened in between. So we're going to focus mostly on the hoof here, but we're going to look at how the horse's hoof and large flat teeth for grazing are some examples of how things change over time. So again, looking at this graph, obviously we've got some horses. Let's look at the timeline here. So we have 50 million years ago down here, 35 million years ago, 15 million, all the way up to modern day horses. So older things down here, and we're getting more modern as we come up. So let's look at the horse feet. All right, so we've got some numbers on here. The numbers indicate essentially digits or fingers. You might know that sometimes we call fingers digits. Um, so, do horses have thumbs? No, they do not. That would be one. So, your thumb is one, your pointer finger is two, your middle finger is three, your ring finger is four, and your pinky finger is five. So, horses sort of have fingers, or at least back 50 million years ago, horses had somewhat of, we could call them fingers, toes, really. Um, and so we can sort of see how that changed over time. Now, here we've got four fingers. Here we've sort of only got three fingers down at the base, and the fifth one, you can maybe see it on your screen, is this little bitty little lump right up here that's not really much of anything at all. It doesn't really do anything up there. So we go from four fingers to three fingers in the course of what, 20-ish million years. Then move up, we still have these three fingers, but now we've got one, that middle finger essentially, that number three, is more developed. And these two on the side here are kind of maybe just hanging out, not really doing much anymore. Here, we're still there. They're essentially sort of walking on three toes. As we move up a little bit further, that two and four, so the index and the ring finger, are sort of moving their way up the leg and not really doing anything anymore. At this point, the horse is really just on that one single digit, essentially the middle finger, the middle toe. And then up here, modern horse, that's what we see. So on a modern horse's hoof is sort of like its fingernail. You might know that. Horse hooves are kind of like fingernails. They do have to be trimmed and cared for. Um, in wild horses, they kind of, I don't know a ton about horses, but I'm pretty sure that in the wild they sort of just wear down naturally. But horses who live in barns and whatnot have to get their feet, their hooves taken care of. So, anyways, that is how a modern horse looks. Pretty much just this one thing, and they've sort of got some, we call them vestigial things. They're just little tiny, probably like tiny bone fragments up there that don't really do anything at all anymore. So yeah, horses pretty much just walk on their middle finger or middle toe. Now let's talk about why these changes would have happened. So that's the change that we see. We go from fingers to essentially one single big finger. Okay. Let's look at this next picture and sort of talk about why that happened. Now, again, we've got a long time ago down here, and we move to modern day up here. Again, we're still just going to be focusing on the feet. So, some other things to understand in addition to older times and modern times, we're going to be tracing the lineage to our modern horse along this yellow line here. So that yellow line shows that this guy was the branch that ended up creating the modern horse. These guys must have sort of gone extinct here at this point. And some of these did. So we can see like this guy doesn't have any modern ancestors, at least not that we're tracing here, but it looks like they just sort of went extinct there. So we see a couple of extinctions happening there. All right, so other important thing to notice about this particular chart is this little key down here, where the green is grazers and the brown is browsers. So browsers are going to live like in woodlands, and grazers are going to be in grasslands. So let's talk about browsers real quick first. So browsers means they sort of live in like a wooded area. They'll maybe eat little soft tips of twigs and like leaf buds, maybe some berries. Maybe they'll sort of sift around in the dirt a little bit, maybe find some like grubs or little things like that. So that's what browsers are. Grazers live in grasslands and they pretty much eat grass. They might eat softer grass or whatever, but so we've got those who live in open grasslands and those who live in more woodland areas. Okay, so keeping that in mind, green is grass, brown is woods. Let's talk about the advantages of the different types of feet. So again, down here we've got our four-toed little horse-like ancestor thingy. Okay, why would those four toes be helpful in the woods? Also, notice how much smaller he is. Okay, so actually, you know what? Let's start by talking about size. So we can see over time, this guy's pretty small, this guy gets a little bit bigger, and so on until our modern day horse is pretty big. Why would it be advantageous to be small in the woods? Well, let's think about if you are prey and you've got a predator chasing you. If you need to run through some dense woods, do you want to be as big as a modern day horse, or do you want to be kind of small? I would want to be kind of small. It's going to be a little bit easier to sort of bob and weave between trees. You don't have this whole giant frame that you have to maneuver through the woods. Maybe you can hide behind something a little bit easier if you're smaller. If you're big like this, there's no hiding that really. So smaller animals are going to be better suited for a wooded type of habitat in that reason. Again, this one's a little bit smaller. Once we get out into the grasslands, we start getting kind of big. We start getting to the size of like deer and stuff. Maybe a little bit bigger, to be honest. I'm not exactly sure how tall that one would be, sort of judging by the sizes of the pictures here. So that's one thing. We're getting bigger as we go. Now, when we're out in the grasslands, you don't, there's nowhere to hide in the grasslands, right? You can run in a straight line as fast as you can away from your whatever's trying to kill you, whatever's trying to hunt you. That's pretty much all you got. There's no bobbing and weaving. There's nothing to hide behind. You just want straight speed. So the advantage here for bigger animals like horses is the length of their legs. For every single step that this leg takes, that's probably what, 3, maybe 4 steps of these tiny legs. So by this horse being really big like that, he can get a lot more speed. Not to mention, I mean, if you don't know, horses kick pretty hard with their back legs. That's kind of a little bit of a defense. He's going to be a little bit harder to take down as a bigger animal, so there might be some other advantages to there. Basically, out in the grassland, there's no reason to be small. There's only good reasons to be big. Now let's talk about the feet a little bit. So again, moving back to olden days when we had the 4 toes, let's think about maneuvering, right? You're bobbing and weaving through the woods. those four little toes are going to grip nicely into the ground as you're weaving around. They're going to maybe conform to the ground as you're turning quickly. Again, we've got some turning happening there. Again, two browsers maybe will dig into the dirt a little bit to get like grubs or little roots or something like that. So those toes are going to be better for digging. Once we get out into the grasslands, though, notice here's where we see that there's still some tiny toes on the outside, but we've still got that main big toe there. When you're in an open grassland and you're looking for speed, one big toe is going to just be, just pure speed. There's no sort of shock absorption that would happen here. When your foot hits the ground, you're off and going. I mean, just think of we have horse races and stuff because that one hoof, that one sort of foot toe thing is just really efficient for speed. Also, these guys aren't digging so much anymore. It's really hard to dig in a grassland. So they're pretty much just eating the grass that's already growing up. They don't have to do much digging. So um, they've just got that one big toe and it works well for them. So main points here are we can see this changing of the anatomy of the horse over time, and we can also see that it changes along with the environment that the horse lives in and the sort of niche that it fits in its habitat. All right, let's look at some other things here. So we're going to look at this guy first, and then we're going to come over and look at the skulls. So looking at this guy, again, let's orient ourselves with the graph a little bit. So we've got, this is in millions of years ago. So 25 million years ago versus 55 million years ago. So older to more modern is on this side. Okay. So where the animals themselves are doesn't matter so much as like where their little branch is on the thing. So anyway, these guys are the older, these guys are the more modern because they're branching more and more to the modern end of things. Okay. So first off, there's a hippopotamus up here. Most of these things we're going to look at are like dolphins and whales. That's sort of where we're headed over here. A hippo, some people call a hippo a land whale, which is pretty appropriate. I mean, they look at them, they kind of look like a whale with legs. They're big and gray and fat, just like whales. It's just that they're on land, so they have legs. They don't swim in the water so much. But hippos are actually good swimmers. If you're ever being chased by a hippo, which I know that happens like all the time in Mishawaka, you're always getting chased by hippos, right? If you're ever getting chased by a hippo, do not go into the water. Hippos can probably swim better than you can. Your best bet, I don't know, is I guess just to run and scream, but they can also run really fast. Hippos are kind of scary. Anyway, let's get back on track here. So, what we're going to be looking at here is the skulls of these animals. Now, these guys over here, what do you think they do? You think they spend most of their time in the water, or do they spend most of their time on land? Well, they've kind of got tails that look like they could be good for swimming, but they're clearly walking on their feet. So to me, that says they are land creatures. And mostly what we're going to be focused on here is the nose. That little spot right there is its nose at the front of its face. Think like a dog. Its nose is at the tip of its snout like that, right? They're land creatures. They just breathe sort of wherever because all of them is open to the air. Okay. Now, as we move a little bit further down, here we can see this guy looks like he still has his legs, kind of like these guys, but they're starting to look more like flippers. So it looks like this guy is more of a water creature, okay? We don't see his skull. Again, water creature, not really seeing a skull for this guy, but we're moving more and more into water creature looking things, less and less like land dwelling. So let's look at this skull. This is the next one we have. This is presumably for this, I don't know how to say that, Rhodectus, something like that. Let's look at where the nose hole is on this guy. So this guy, he still does have some feet. Maybe he'll come up to land occasionally, but definitely looks more like he's a swimmer, right? He's definitely got that swimming motion going on. Look at where its nose hole is now. What happened to it? Here, it was like right at the very tip. Now it's not so much at the tip anymore. It's almost moving back a little bit. It's sort of on the top of the snout now. Here you can even see the little indentation there. That's where it is. It's sort of above sort of the mouth. Here you can see that little indentation is right sort of again at the front. It's moving backwards on the skull. Okay, here we have something that's looking a lot like a dolphin. We're not quite, here's our dolphin, so we're not quite there yet, but it's looking a lot like a dolphin. And let's look at where the nose is there. Look at, again, it's even further, again, sort of on top of the mouth. It's almost halfway between the front of the skull and the back of the skull. So it's moved back quite a bit. Again, we can see the little indentation from this view. It's almost in the back half of the top of the mouth now. So again, we can see that nose hole moving back further and further to our modern day things, okay? This is the nose hole now. It's like in between the eyes. It's on top of the head, okay? It's like right here on this image. So why would something that lives in the water want a nose hole, a blowhole? Once we're getting into these guys, we call them blowholes now. They're not really noses anymore. Why would we want that on the top of the head? Well, if you think about it, think of, again, comparing these guys up here to more of like a dog. What if a dog was underwater and had to just stick the top of its nose, just had to stick its nose out of the water to breathe? Think of how it would have to bend its head sort of backwards and up in order to stick its nose out. It'd be a lot more convenient if its nose was on the top of its head, so it wouldn't have to crane its neck crazy in order to poke its nose out of the water. That's what's going on with these guys. These guys don't have to bend backwards, literally bend backwards, to get their noses out of the water because their nose is already on top of their head and it's efficiently allowing them to breathe. Keep in mind these guys are mammals. Mammals breathe, so they're a little bit different than fish. Fish have gills. They don't need to worry about breathing air. They exchange oxygen through the water itself. So that's what's unique about these guys, is that they still do need to breathe air even though they spend all their time in the water. Okay, so we can see the changing of the skulls to suit their environment. Again, more land, going more to water. Their skulls change over time and evolve into different creatures to suit their environment. Now, let's talk about this guy over here. So we've got these like humanoid skulls. You might be able to guess. These guys over here are the more ancient, and we're getting to more modern as we go to over here. So this one over here is a modern day human. Okay, let's talk about the changes we see as we go from left to right. So the first big thing that I see is a change in jaw size. All right, so let's look at the jaw on this guy. It's really big, really stout. I would not want to be bitten by this thing right here. Let's look at this jaw over here. It's kind of almost tiny, at least in comparison to this guy over here. And if we watch over time, we can sort of see that jaw getting a little bit smaller and smaller over time, right? The next thing I want to look at is the area where our brain goes. This is the size of a modern day human brain cavity, pretty big in comparison to the head, getting maybe a little bit smaller and smaller and smaller as we go back in time to right here. Now, overall, the head size stays roughly the same, right? We could say they're all maybe basketball sized, okay? There's no significant difference in general size of the head. Why would that be? Why are we not getting any bigger or any smaller as far as our head goes? Well, let's think about being born, right? At some point, we all had to fit out of a certain area of our mom, okay? And there's bone. We had to fit basically through our mom's pelvis. Now, there's a certain sized hole in a woman's pelvis that an entire baby human has to fit out of. Imagine if its head was too big. It wouldn't fit very well, right? Not only could that be harmful to the baby, getting squished too much, it could even kill the mom, right? And so there's problems associated essentially with having too big of a head, basically. So that is why our head size stays about the same, because our pelvis size has stayed about the same, and there's a limit to how big the head can be and still fit through the mother's pelvis. Okay. If your head was too big, you maybe would die at birth. You couldn't pass on that big head trait. Again, natural selection. If your mom, was made too big of a baby head in her womb, she would die. She wouldn't be able to have any more babies, and make her gene to make a big baby head maybe wouldn't exist anymore. So anyway, big head, no good for humans. All right. So thinking again about how our jaws have gotten smaller and our brains have gotten bigger. Okay. Let's think about the things that allowed our jaw to get smaller. And as you watched that video about evolution last week, you maybe remember seeing some of this. Remember when we made fire? When those humans in that video, do you remember when us humankind made fire? I do. No, I'm not that old. If you remember in the video when those humans made fire, all of a sudden, when they cooked a little bit of that meat, it became easier to chew. The jaw didn't need to be as big and as crazy to chew through raw meat. As we cooked the meat, it got softer. As we cooked our food, imagine eating a raw carrot versus a cooked carrot. Okay, we learned how to cook things. We learned how to essentially make our food softer, which allowed our jaw to get smaller. Now, our jaw getting smaller, imagine if we had this size of a jaw with this size of a brain cavity. Our head would be tiny. But making that smaller jaw allowed more room for brain, essentially. So over time, our brains could get bigger and bigger and bigger because our jaws got smaller and smaller and smaller. So even in human skulls, we can see the changes through things over time. Okay. I believe, oh no, I think there's a couple more. So let's talk about the law of superposition. I'll try to get through this quickly. I know this video is getting long. Law of superposition is pretty simple. Basically, it's saying that the new rock layers are deposited on top of the old ones. The oldest stuff is near the bottom, okay? Kind of makes sense. So you've got some grass here. This grass dies, decomposes, becomes dirt, gets deposited as dirt on top. Now more grass grows on top of that dirt, dies, decomposes, is a new layer of soil. New grass grows on top of that. So we have our oldest soil down here and our youngest up here. I often compare it to, say you want to wear this particular shirt that you haven't seen in a really long time, and your floor is piled up with your clothes all over the place. I used to be bad about this. I've gotten a little bit better. But if there's a thing, I haven't seen in a long time, I know that it's probably further down, deeper in my pile of clothes on my floor, whereas the shirts I wore yesterday are up here. It's a law of superposition. Newer things on top, older things on the bottom. So looking at this picture right here, we can guess that of these 4 fossils we see, this one is probably going to be the most recent one, and this one is probably going to be the oldest one, because new things don't just shove their way down into the ground. Things get deposited on top and on top and on top, and so deeper things are older things, basically. Now, sometimes we do have human manipulation of things getting tossed around and whatnot. So we have these things that we call index fossils. Index fossils are fossils that essentially we can relate to a certain area in time. So here we have A, B, C, and D. So this goes in order. We're pretty confident there. But here we're missing layer B. Here we only have layer A. Here we're missing layer D. So how do we know, this is on top, so this must be the most recent, right? But this is also on top, so this must be recent, right? But it's not, because this is back in layer A. So an index fossil essentially tells us what layer we're looking at. So if you look through this, for instance, this little thing looks like a cockroach. We only see that in layer A. So if we find a fossil next to one of these little cockroach thingies, we can assume that those are both from this deep down layer. Now, however, look at this little, whatever, this almost looks like a moth shape here. We also see that up here in layer C. But because that little moth-shaped thing isn't next to a little cockroach-looking thing, we don't exactly know how old it is, okay? Essentially, we can use this cockroach thing as an index fossil to know this layer. The little moth thing would not be a good index fossil because we see it in multiple layers, okay? If I find, this little spiky thing next to the moth thing, it doesn't tell me anything about which layer it originally would belong in, because I see a moth shaped thing here and I see a moth shaped thing here. So this moth shaped thing is not a good index fossil. Index fossils are essentially fossils that we only find on one layer, like the cockroach guy, that can tell us the age of other fossils that we find nearby it. Okay, so index fossils sort of help us know the age of things around it because they're unique to their particular layer. Finally, there's one last thing I want to talk about before we move on. We can use also a thing called radioactive dating or carbon dating. You may have heard of that. That talks about how old a particular fossil is. Okay. So basically, radioactive elements are present in everything. There's different types of carbon that you can have. Essentially, you may have heard of carbon 12, carbon 13, carbon 14. Some of them are more radioactive than others, and they decay or go away at a constant slow rate. So the fewer radioactive elements we find in a sample, the older it is. You don't need to know all the ins and outs of this. I just want you to know that it exists and that it does work and that it is very reliable. Okay, so basically the more, so we're talking carbon 14 here. It's a particular type of carbon that is radioactive. If you have a lot of that, if you have a lot of carbon 14 present, you're probably pretty new. This is 0 years elapsed. Okay, you're probably pretty new. As we go through time, as more and more years pass, that amount of carbon 14 goes down and down and down. So if I find a thing that I find has a very low percentage of carbon 14, I can assume that it's really old, and I can actually find a specific percent and match it to a certain amount of years that have gone by since it was living. Okay. If it has only this amount and doesn't have a whole lot of carbon 14, but it has some, I can match that percent to a certain amount of years past. So again, you don't need to know the ins and outs, just want you to know that it exists. All right, we're going to call that the end of part 2. Come back tomorrow for part 3. If you have any questions, as usual, let me know. Don't forget there is that quiz in Canvas that you need to do along with this. All right, we'll see you tomorrow.